Hello and welcome to RRS Live 2024. I'm Lawson McVay. I'm an undergraduate student majoring in aerospace engineering and physics. My project director is Dr. Sichen Yuan in the Department of Aerospace Engineering and Mechanics. My presentation is on the Aranea Debris Interceptor, a biomimetic approach to orbital debris mitigation. The outline of the presentation begins with the motivation. First, we examine something called Kessler syndrome. Space debris is an issue, as you may have heard. Kessler syndrome is the proposed term for a cascading sequence of orbital debris. This is when debris collides with other pieces of debris, creating even more particulate in orbit. This is independent of new launches. It's unclear how exactly Kessler syndrome might proceed. The European Space Administration, or ESA, predicts largely exponential growth of debris, while NASA's simulations have linear predictions of debris accumulation. Current models vary on how exactly Kessler syndrome may precipitate. However, the concept is surely sound. In 2009, an Iridium communications satellite collided with a Russian satellite in orbit. That impact generated around 2,000 pieces of debris, at least 10 centimeters in diameter. Through ballistic testing of matter at high velocities characteristic of orbital motion, as well as observation of orbital initiatives like the International Space Station and the Hubble telescope, it's evident that even small particulate has the ability to severely damage and even destroy operations at sufficiently high velocity. If Kessler syndrome were to crystallize, it would essentially lock humanity out of specific orbits, if not out of space entry entirely, as well as hamstringing the satellite communications operations as we know them today, which are responsible for things like GPS and high-speed internet communication. NASA's cataloged thousands of pieces of space debris with diameters of at least 10 centimeters in various orbits around Earth. As we continue to launch more and more missions into orbit, older missions become defunct and essentially nothing more than debris themselves. Relying on Earth's gravitational well and in lower orbits atmospheric drag, deorbit times can be on the order of decades. As missions continue to launch, debris continues to accumulate, and we could soon run into a major problem if that Kessler syndrome were to materialize. Our solution for orbital debris is the Aranea Debris Interceptor. Taking inspiration from nature to solve engineering problems is known as biomimetic design. Inventions like Velcro and advancements in fields as diverse as aerodynamics, neuroscience, and mechatronics have all been benefited by this principle. The name and inspiration for this spacecraft, the Aranea Debris Interceptor, or ADI, comes from the ogre-faced spider, which spins a web between its front legs and lurches forward towards its prey to capture it. Similarly, the ADI will fabricate a net in space environment using tensegrity-based robotic arms. The spacecraft can then perform a forwards capture of debris or a backwards capture of debris. In theory, having a couple different capturing techniques can increase efficiency, since different types of debris may be more or less suited to one type of capture. Finally, the ADI will attach a drag sail to the captured debris, facilitating much faster auto-deorbiting times with atmospheric drag having a larger role than gravity. The ADI will also feature its own solar sail, allowing the spacecraft to move between different orbits. Ideally, this could be used to target specific pieces of debris, such as recently decommissioned satellites that may pose a hazard, but could be deorbited before fragmentation. The spacecraft design hinges on the deployable tensegrity arms, which is where my research focuses specifically. Tensegrity is the structural principle where isolated members, or struts, are suspended in a pre-stressed tension framework, or cables. The benefit of using tensegrity is its intrinsic lightweight properties. Due to the low gravity in orbit, the weight of the spacecraft doesn't matter much in the space environment, except for maybe inertial concerns. However, it's imperative that spacecraft is lightweight because when things like fabrication and launch costs are evaluated, heavier missions are much more expensive to launch into orbit. We use a tensegrity concept called clustered tensegrity, where cables are continuous up and down the length of the structure in order to provide up to 8 degrees of freedom and an efficient mechanism for expansion and retraction of the robot arm from just one motor at the base of each joint. Another benefit of tensegrity is the high stiffness to mass ratio, allowing for precise and efficient mechanical control of the arms, which is absolutely necessary, especially in the net fabrication stage of the capture process. The current state of the work is a 3D printed model. The struts are plastic filament, and the cables are composed of 30-pound fishing wire. The clustered cables pictured here are the vertical or longitudinal cables, which would be the expansion and retraction mechanism for the arm. The latitudinal cables currently are in a non-clustered, discontinuous state. The strut and cable joints are jewelry eye hooks. The actual kind of integrity of the structure doesn't matter because all it does is essentially verify the stability of this tensegrity geometry outside of a mathematical model. Our future work mostly focuses on the investigation of the deployment mechanism and adjustability. When the longitudinal cables are expanded or retracted, the latitudinal cables necessarily expand or retract as well. If the cables are kept in the discontinuous state, each segment will need 4 actuation systems per unit. If continuous, they should theoretically require only 1. Investigation into both the possibility of using clustered latitudinal cables as well as possible actuation mechanisms such as pneumatics, hydraulics, or mechanical linear actuators is ongoing. Other areas of future work include fabricating prototypes with metal instead of plastic filament, as well as developing a control scheme for overall spacecraft behavior and the fabrication of the debris net. All right, thank you for your time. Any questions?
So why was this tensegrity geometry chosen?
Right. So the tensegrity geometry, as you can see here, is pretty sparse, especially when compared to something like a solid arm structure that you might see in like a surgical lamp, right? You can think of those 2 posts as basically solid material. So this essentially makes the structure more lightweight, which again would make those launch costs and operation costs much cheaper.
You mentioned Kessler syndrome and the motivation for your work. Could you explain what the timeline is for that?
So currently, according to predictions by the ESA and NASA, we really don't have a timeline. There's a possibility that we're already in the beginning stages of Kessler syndrome, where things are continuing to fragment, and collision events such as the 2009 satellite impact are only going to get more common from here. There's also a possibility that it hasn't happened yet. There's a small possibility that it's not even a possibility, but current models suggest that it is. Unfortunately, we don't have a way of knowing exactly when it might precipitate, but it's important to get ahead of that. So launching this or some other orbital debris mitigation mechanism is imperative.
So you mentioned that this was built, the physical model was built in order to test the validity of the mathematical model, or to test the validity of the structure outside of a mathematical model. Could you describe how the structure was first conceived of, like within the mathematical model?
Sure. So tensegrity has been around for a while now. We know several different geometries that are stable. Clustered cables are relatively new, especially in the engineering context. So just making sure that this was going to be applicable for this particular circumstance was necessary. This model, which has 4 struts per unit, was chosen mostly for that degree of freedom that I mentioned earlier. If one longitudinal cable was retracted faster or more than the other 3, then that could result in a bending of the arm, which might be desirable in certain debris capturing scenarios.